the billet and slab. Then we have talked about the difference between plate, seat, then powder rolling mill. With the help of the rolling mill, also how we can use the powder. Then in the last, we have talked about the rolling mill, variety types of rolling mill. We have two high roll mill, then three high, then four high. Then also we have talked about the cluster rolling mill, then the we have covered. Maybe apart from this also we have covered the universal mill and pendulum mill. Okay, so these are all we have covered. And today we will talk about little the mechanism part, how or the the calculation, how we will make. For example, if one metal piece we are passing from one end, then when it is going towards the other end, how it is reacting, how it is affecting. So the basic title today we will talk about the flat rolling and the analysis. When we are making we are taking the assumption of the flat rolling, then how the analysis we can make it. Okay, so flat rolling involves the rolling of the slab, strip and seat and plates also what we had discussed in the beginning of the classes. Then box part of rectangular cross section in which width is greater than the thickness. Normally when we are talking about this sheet, for example, if we are talking, so from here to here, this is length of the sheet what we are taking, and this is the thickness. Okay, the small height is the thickness, and this area or this side is known as the width. Okay, so three things are there. And in flat rolling, the work is squeezed between two rolls. Whenever we are talking about the flat rolling, the whatever the workpiece you have or whatever the material you have, these are squeezing between the two rolls so that its thickness, whatever the initial thickness you had, and whatever you are getting the after the thickness, and this reduction is known as the draft. Okay, for example, initially you can see here in the bottom of the picture, your initial thickness was T0 and your final thickness you are getting TF. Okay, and whenever you are making the a minus or the reduction, that means T0 minus TF is known as the trap. Okay, so here I mentioned D equal to T0 minus TF, where T is known as the trap, and this is a unit you can take as a millimeter. T0 is known as the starting thickness, and TF is the final thickness, right? And the drag is sometimes expressed as a fraction of the starting stock thickness called as a reduction. Okay, so if you take the reduction, if you define the reduction, this R equal to whatever the draft we got here divided by the initial thickness of the material. Okay, this is known as the reduction. So two things now we got. One is draft. This draft equal to initial thickness minus the final thickness. Whereas we have, if we are talking about the reduction, this reduction equal to the draft whatever we have received here divided by the initial thickness. Right? Is it clear?
Yes, sir.
Fine. And when series of the rolling operation are used, because sometimes I told in the previous classes also, instead to take one kind of rolling operation, because if you want to make a lot of sample or lot of product together, so when that means when we have series of rolling operation are used, the reduction if you want to find out taken as the sum of the draft, whatever the sum of the draft divided by the original thickness, because here we have taken only one draft. But if you have a series of operation, then you have to add all the drafts divided by the initial or the original thickness you want to take. In addition to thickness reduction, rolling usually increases the work width. So whatever I told here, the width, for example, this side, okay, the width also whenever you are making the rolling, the width also it will increase from the initial position to final position. For example, you will take W0 to WF, and this is known as the spreading. Okay, so that means when you are reducing the thickness is known as the drag. When you are reducing the width, it is known as the spreading. And it tends to be most pronounced with low width to thickness ratio and low coefficient of friction. At the same time, also we have to find out maybe friction is there, and the moment you have the friction also, how it will impact, how it will generate there. And the conservation of materials preserves the volume of the metal exited at the rolls equal to the volume entered. So initially, like, in forging also what we have discussed, like initial volume what we have, the after the forging also the similar volume we will get. Similarly here also, whenever we are talking about the rolling, whatever the initial volume we had, and when after the rolling also, we will find out the same volume. So here what we, if we have the volume, we are considering T0 into W0 into L0. So that means the thickness you have, this width you have, and the length you have equal to TF, WF, and LF. Fine. The initial volume equal to the final volume. Okay. Yeah. So if you see again the same schematic diagram, I just put in all the slides to better to understand, and where the W0 and WF are the before and after the width. Whatever the initial width you have taken as W0, and whatever the WF width, this you are taking as the after the ruling. And whereas the L0 and LF are the before and after the work length. Whatever the initial length you have L0, and after because the length is also changing because whenever you are squeezing. So LF is known as the length after the roll. Okay, so now we have to understand that the velocity also, or the roll speed, or the velocity of the workpiece also, that we have to consider. Similarly, before and after volume rates, okay, of the material flow. We are talking about the material flow. Maybe later also it will come the velocity of the roll also, because two things you have to remember. Do not be confused. Similarly, before and after the volume rates of the material flow must be the same. So the before and after velocities can be related as T0, W0, and V0. So V0 is the initial velocity of the worksheet equal to TF, W, and VF. And VF is known as the velocity of the workflow or the work after the the rolling, right? And here also I have mentioned why actually we are talking about T0, W0, V0 equal to TF, WF into VF, where the V0 and VF are the entering and exiting velocity of the bulb. Okay, so that means this is only the velocity of the workpiece only. This is not the velocity of the roll or the rolling mill. Fine, is it clear?
Yes, sir.
Okay, and the rolls contact, and if you can clearly see the picture here, how to find out this angle theta. Here you can see the theta is known as the roll contact with the work along an arc defined by an angle theta. Okay, for example, you can see here the material piece whenever you are putting to the rolling wheel, you can see you have the vertical line here, and if this angle, if you will make this angle to the touch of the workpiece to the rolling mill and to the vertical, and this angle is known as the theta. Okay, and of course you can make it in forging also. We have derived, for example, tan theta equal to this by this. Okay, that also you can find out. And each roll has a radius r, and whatever we have two rolls here, and this roll radius is r, and this roll radius is r, and its rotational speed gives its surface velocity vr. Okay, so now you have three things. One is V0, and one is VF, and one is VF. So every time, that's why I'm in the exam also I'm asking that you have to write this very clearly. Because if you write just A0, V0, and W0 equal to A0, AF, VF, and W, then what should I know? What is AF? What is A0? Because many confusions are there. So you have to write the surface velocity of the roll, or the roll velocity, or the roller velocity is known as the VR. And this velocity is greater than the entering speed of the work V0 and less than its existing speed of VF. Okay, and whatever the roll speed you have, and this depends upon the material flow, because here you can see whenever you are pressing here, you will create, or you will find some resistance there, or the friction is there, right? And since the metal flow is continuous, there is a gradual change in velocity to work between the rolls. And the moment you have the material is flowing from one end to the another end, automatically your flow is also, or the velocity also, it will try to decrease, because here you are pressing here, right? And the moment you are pressing, you are generating some friction there. Okay, but the other side, of course, you will find some friction there, but this material flow will be a little there is some gap here. Okay, so both the velocity will be different there, and this difference is known as the no slip point, also known as the neutral point. Okay, and the moment you have, the one point, the arc work velocity, whatever the work velocity you have, or the material velocity, and the roll velocity is similar or is equal, and that point is known as the no slip point, or the neutral. On either side of the point, slipping and the friction occur. So the moment you have the material flow and the material piece within the two rolls, so you will find some friction there. And the amount of slip between the rolls and the work can be measured by means of the forward slip. And this S is known as the forward slip, and this equal to VF. So that means the final velocity of the workpiece minus the VR. This is the roll velocity divided by the VR, right? So S equal to the forward slip, and VF equal to the final velocity, and VR equal to the roll speed, or the roll velocity. Fine, is it clear? Yeah, is it clear?
Yes, sir.
Any- oh, So now these things also, when we are talking about the true strain also, these are the similar what we had done in the forging also, the true strain experienced by the work in rolling. So the epsilon equal to ln T0 divided by Tf, where T0 equal to the initial thickness and Tf equal to the final thickness. And the true strain can be used to determine the average flow stress. And the moment you want to find out the average flow stress, this is equal to K epsilon to the power n divided by 1 plus n, where K equal to the strength coefficient, right? And also, when we are talking about the friction or the resistance, also we have to think about the D max. Okay, so what is D max now? So initially we have discussed here. Okay, so the D draft equal to the initial thickness minus the final thickness. So similarly here also, if you want to find out the D max equal to mu square into R, and where D max equal to the maximum draft here, and mu equal to the coefficient of friction, and R equal to the roll factors. Okay, so this is one more equation you have to find out. And the equation indicates that if friction were zero, if you have the friction is zero, then of course the draft will be zero. Okay, so this is like directly proportional to the friction is directly proportional to the maximum draft. Okay. So next we have now what are the parameter actually when we are talking about the friction. So the coefficient of friction in rolling depends upon the lubrication, also the work material, also the working temperature. Because the three things again what we have discussed in forcing, the similar we also we have to discuss. And in cold rolling, the value of around 0.1, whatever you have the friction actually, in cold rolling you have to consider a 0.1 in warm working, this is you have to consider 0.2, and in hot rolling, this is you have to consider 0.4. Okay, but sometimes what happen, you have to find out because you cannot tell that every time, whatever the material piece we are putting, this is for all the material, it will be same. You cannot find. So sometimes the hot rolling is often characterized by a condition called known as sticking, because sometimes you will find some stick here, in which the hot work surface adheres to the rolls over the contractor. Okay, so sometimes if you want to find out some stick or if you are getting there some stick, then at that time the coefficient of friction or the mu you have to consider as 0.7. And this is normally happening in case of steels or the high temperature alloy, because it will not pass easily. So you will find some adhere there or you will find some stick there. So that process is known as the sticking. And the consequences of sticking is that the surface layer of the work are restricted to move at the same speed as the roll speed layer. And below the surface, and you have to find out the force actually, the rolling force. The rolling force equal to W integration 0 L PdL, where F equal to the rolling force and W is known as the width, whatever we have discussed earlier, and P equal to the roll pressure and L equal to the length of the contact rolls. Okay, so this L equal to this one. So you have now three things. One is L0, initial length, LF equal to the final length, and this L equal to the contact length from here to here. So actually this is written in that on a curve line, but this length you have to take parallel from here to here and you can make a horizontal line. Okay, so this length is known as the contact length. And the integration requires two separate terms, one for each side of the no slip. So that means one is you have to take two types of integration. One is in the left hand side, and the second part you have to take in the right hand side. Then again you have to consider, because in the left hand side it's a different aspect, and the second hand side or the right hand side you have the another aspect. So variation in roll pressure along the contact length is significant. So you have to think about the roll pressure. That is much more important here, because the moment you have how the roll pressure you are creating, because the moment you have the friction here, so that means your roll pressure is also increasing. And the roll pressure you are increasing here in the left hand side, and at the same time also the moment you are getting the friction here in the right hand side, also you are creating some roll pressure there. So that's why you have to take two integration. One is in the left hand side and one in the right hand side. Fine? Is it clear?
Yes, sir.
Okay. So maybe one more slide we will talk, then we can stop. We will do the numerical in the next class. Okay, so now if you want to find out the whatever the flow stress you have, so now the force also you have calculated. So now if you want to find out the roll gap if you have, so the approximation of the results obtained from the previous can be calculated based on the average flow stress. So if you can calculate F equal to the flow stress into W into L. Okay, and the product WL is the roll work contact area, because this is the width into the length you have. So this is known as the contact area. And the contact length, if you want to calculate the L equal to whatever the radius of the roll into T0 minus TF, or you can consider as the D max. Okay, the draft you have, and to the root over to the power 0.5 or maybe half. Okay, these two equations also you have to remember. Okay, so finally this last slide we have, when we will calculate the torque also, the torque in rolling can be estimated by assuming that the roll force is centered on the core as it passes the rolls, that it acts with the moment arm of 1/2 of the contact of the length. So this torque equal to 0.5 into the force into the length of contact between the two rolls. Okay, so every time you have to, do not be confused again with L is not equal to L0 or LM. Okay, so this is known as the length of contact between the roll and the workpiece. Okay, so similarly, if you want to find out the angular velocity also, you know this one. These are already we have done in the previous classes, 2 pi n, where n equal to the rotation speed of the roll, and the power for each roll equal to 2 pi n into the t. T is known as the torque, right? And the last we have, if you want to convert this, whatever the torque you have here, if you want to convert to as pressure equal to 2 pi n f into L, where already we have derived n equal to the rotational speed of the roll, f equal to the rolling force, and L equal to the length of contact between the rolls and the workpiece. Okay, so these are all the equations we have, maybe 6-7 equations you have. Please go through carefully. And from tomorrow's class, we will make 2 or 3 numericals. Fine.
Yes, sir.
Any other question up to now?